Well, good afternoon to you all, and thanks to Michel and Pierre-Andre for setting this up and for asking me to talk about the Portsdown test equipment. For those of you who don't know me, I'm Dave, GKQ. I started, along with Noel, the Portsdown project about 7 or 8 years ago, building on the excellent work done by Evereast F50EO. But specifically today I'm going to talk about the Portsdown test equipment. So without further ado, let's start. First of all, I'm going to talk about the hardware, what the capabilities are of the complete hardware, and then specifically look at the test equipment and some of the ways we can control it. Portsdown for our hardware is pretty simple really. It's a Raspberry Pi 4, not a 5 at the moment, Raspberry Pi 4, and a 7-inch touchscreen. They connect together with ribbon cable and allow you to control the Raspberry Pi really easily. The basic capabilities, we've got it started off as a DVB-S transmitter, went to DVB-S2 and added DVB-T. Thanks to some excellent work by Heather, M0HMO, we've managed to add a receiver in, and some further work from Charles, we've got a DVB-T receiver in as well. Colin G4EML has written some software that enables the same platform to do FM, CW and SSB. That's the Langstone. Not going to talk about that at all today, but it's worth looking up for you. It'll also handle video streams, but the main thing we're going to talk about today is the test equipment. Once you've built it, you can explore the utilities that are there, things like calculating range and bearing from locators and so on. You can build it any way you want. You do need a 7-inch touchscreen or possibly a 5-inch touchscreen using a DSI connector. It will not work with the old 3.5-inch touchscreen that we had on the Portsdown 2020. But how you build it is up to you. Without further ado then, on to the test equipment. Built up quite a suite over the years. Band viewer, I think, is the headline one. A signal generator, a means of measuring noise figure, a means of measuring noise and carrier level, an add-on for a power meter, a frequency sweeper for sweeping filters, an XY display for those old spectrum analyzers, and a DMM, a digital multimeter display and logger. So the most valuable tool I find is Band Viewer. Now this is essentially a narrow sweep spectrum analyzer using an SDR. There's a choice of 5 SDRs, Lime SDR, USB or Mini, Pluto. It'll work with an RSPDX version 1, not the version 2 yet. An AirSpy R2 or even an RTL SDR. Using those, the whole suite of SDRs, you can cover 2 megs to 30 gigs. But its primary use, what it was designed for, is as a pan adapter on receive for ATV. And it will give you very accurate relative levels, but the dynamic range is simply limited by the SDR, so the RTL SDR isn't as good. So this is what it was designed for doing weak signal work. This is a screenshot I took when I was out on a hilltop in a contest a couple of years ago. And you can see 2 humps there. The middle hump is 333 kilosymbols. Don't know who that was. I think it was Colin G4KLB, but I've never been able to find out. And on the left hand side there is a very small 125 kilosymbol hump. Now that initially didn't give any decodes with Minituner, but I knew it was there, and this is the great thing, it brings back the analog aspect to digital ATV. You can see if somebody is there. And in due course we had the right aircraft flying the right track, and the flutter brought the signal up enough for long enough for me to get pictures from Rob at 400 kilometres away on 70 SEMS. Now, we'd never have achieved that if I hadn't known his signals were there by using band viewer. So that's primarily what we use it for. This is the setup I use it with, and this was in the contest a couple of weeks ago. I've got what I call a Portsdown double, and on the left hand side there is band viewer. You can't see the screen very well, but there is a signal in the middle there. And on the right hand side is another Portsdown with a receiver, and that's receiving pictures from Gareth G4XAT on 24 gigs. So it's good for picking up dishes, aerials, whatever. It will also do peak hold if you're monitoring a band. You can't really see it very well on this slide, I'm afraid, but you can just see some red dots there, and that'll just peak hold whatever signals come up. So if you know you've got a carrier coming up somewhere in the band, but you never manage to quite see it when it's there, peak hold will catch it for you. If you use a Pluto, you can get a full 50 meg span on this. Pluto is the most capable in terms of wide span width. Lime SDR gives you 20 megs. AirSpy and RSPDX give you 10, and RTL SDR only gives you 2 megs. And they all differ at the other end of the scale as well. The best on that is the Lime SDR, where you can wind it out to 100 kilohertz wide. The Pluto only goes down to 2 megs. I've recently added a waterfall capability, and you can switch the display between being a waterfall, a mix, which is what I'm showing here, or full spectrum. So that's band viewer. Simply plug an SDR into the USB socket on the side of the Raspberry Pi with the Portsdown software. Next one is the signal generator. This is essentially an interface to whatever you plug into the RTL into the Raspberry Pi. I've put in some approximate amplitude calibration. It's just using lookup tables. The sources aren't necessarily clean. They're as clean as the SDR or whatever you're using. And with different sources, you can cover 1 Hertz to 30 gigs with this. It was originally designed with the Lime SDR, which of course covers from 70 megs to 3.5 gigs. But it also works with the Pluto up to 6 gigs. And thanks to some research by Colin G4EML, we've found that the Pluto has a very significant fifth harmonic. So you can also control that by directly entering the frequency, and it'll give an output up to 30 gigs. Very low level, but great for checking receivers, especially at 24 gigs. You can use an ADF4351 from eBay. That'll work up to 4.4 gigs. The more expensive ADF5355 will also work up to 13 gigs. Down at the lower end, you can use an ADF 9850, and that'll give you anything from 1 Hertz to about 50 megs. And on the specialist side of the house, it'll drive an LCOM source, which is a high stability, low phase noise source available on the surplus market. And it'll also drive a Nort SLO, which are sold by an Italian company who go to ham radio. I've got 3 or 4 of these sources in the 10 and 11 gig range, and they're really useful, but only fairly narrow. This is what the control panel looks like. You just touch the plus or minus buttons to change the frequency. And if you can adjust the level, I mean, clearly on an ADF 9850 you can't adjust the level, but on a Lime SDR or a Pluto you can. If you want to adjust the level, you simply press the plus and minus arrows next to the dBm setting there. So really simple touchscreen interface. A lot of my kit is built up from ex-surplus stuff. This was an AD 9850 I cut out of something else. You can see a roughly hacked printed circuit board, but that works a treat. So it doesn't need to be all neat and tidy. Excuse me a minute. The next thing we've got is noise figure indication. Using a Lime SDR and a switched noise source, you can measure noise figure of receivers and preamps by measuring the average noise power. It also recently I've added the Pluto to SDRs you can use with it. So this is how it's done. Essentially we use the a GPIO on the Raspberry Pi to switch noise source. You need a noise source power supply unit to do that. Preferably a ex-commercial noise source, although there are some available on the amateur market. Into your device under test, and then you use the Lime SDR to look at the RF coming out, and this means you can look at down converted RF from 24 gigs or something like that. Now it's a bit of a black art measuring noise figure. To do it accurately, your SDR must be operating in the linear region. You shouldn't have any other signals around in the shack or even locally. Particularly a problem if you're checking noise figure on 2.4 gigs. Think about what bandwidth you want to measure the noise figure in. If you're measuring something on 144 megs low noise preamp, you might only have low noise performance over 500 kilohertz. And make sure you haven't got any digital noise sources locally, and the Lime SDR itself is particularly bad for this. Choice of noise source. Well, they're quite calibrated noise sources are quite rare. But there's a UK company called RF Design who do something called a BBgen, which does broadband noise from up to 5 gigs at a reasonable price. So, or you can homebrew something. Clearly calibration of those is quite an issue. Most noise sources need 28 volts, not a common voltage in around the Raspberry Pi. So BATC have designed a PCB which has an up converter and the switching circuitry on it. Quite a simple PCB thanks to Mike G0MJW, and all the details of this are on the BATC wiki. So this is what the application looks like. You've got a meter scale on the right hand side there. It doesn't dance around all over the place. It's got ballistics, so it's fairly slow to move. A spectrum view on the top left side, so you can see if there are any signals interfering with your measurement. And then just parameters underneath as to what the noise on and noise off figures are, and these allow you to set the Lime SDR into the linear region by adjusting the gain. You can also calibrate it to say, okay, without my device under test, the noise figure is this and the gain through the system is this. You then press the calibrate button and you'll end up with it saying noise figure is 0 and the gain is 0. But if you then put your device under test in circuit, it'll tell you exactly what the device noise figure is and the device gain. This is my 77 preamp with about 0.8 dB noise figure and about 23 dB of gain. Now 0.8 dB, well, I reckon that's anything plus or minus half a dB. So I think that's about 1 dB noise figure. That's good enough for 77s, that's for sure. So it's not really an exact science. I reckon the errors in this are between plus or minus half and plus or minus 1 dB. But the great thing it will do, it'll enable you to make day-to-day comparisons and to optimize things. You know, snowflaking or just simple tuning. Watch out for digital noise coming from the Lime SDR. You'll see there's quite a lot of that. Use some attenuators for error checking. If you put a 3 dB attenuator in between the noise source and your device under test, the noise figure should go up by 3 dBs. If it doesn't, you've got some inaccuracies in the system, or your attenuator isn't a 3 dB attenuator. The other thing is, some noise sources, the VSWR changes between noise source on and noise source off. So if you've got a 15 dB noise source, you probably want to put a decent 10 dB attenuator after it to reduce that effect. A variation on the noise figure meter is a noise level meter, and this will indicate average noise power within a set bandwidth, either absolute or relative to another bandwidth. And it will also do a carrier level, either absolute or relative to noise over a bandwidth. It works with the Pluto and the Lime SDR. And one of the main applications for this is setting up your kit for receiving ham TV on the ISS. It'll enable you to measure the sun noise you get in your 2.395 gig receiver for the ISS. And here at the bottom right there, I've put in a time plot of the meter reading. So you can see on there are a couple of plots with a side lobe and the main lobe, and the side lobe again, and that was me sweeping the dish across the sun. And you can see I've got about 3 dB of sun noise as I sweep past the sun. So this enables you to check sun noise. So that's the absolute measurement. For the relative measurement, you can measure how high a broadband noise source, such as a DVB-S transmission, is above the noise. So if you're tweaking an aerial for tweaking element lengths or spacings on an aerial, and you've got a distant ATV repeater, you can use this to peak up the aerial in rather the same way as you'd peak up MER. If it's an ATV signal, peaking up on MER is probably nearly as good. It'll also do carrier to noise, and what it does, it picks out the highest carrier in the right hand shaded region of bandwidth there, puts a green line on it to show you which carrier it's measuring. It averages the level with a time average, and actually in the time plot there you can see the effect of the averaging. It's quite long smoothing, but it does allow you to make carrier measurements to about plus or minus 0.1 of a dB and make really fine adjustments. In a similar way, you can do absolute carrier level, so not comparing it to noise, just doing an absolute level. And as I say, that works with both the Pluto and the Lime SDR. Another thing it'll do is work as an analog to digital converter and display for the AD8318 power sensor, which is a cheap eBay power sensor, but does cover up to 7 or 8 gigs quite nicely. And it works along with a MCP3002 analog to digital converter. Connects to the Raspberry Pi by SPI into the GPIO pins. Very simple circuit. Power sensor module on the left. There's a couple of voltage regulators at the top there, and the MCP3002 connected to the Raspberry Pi. And this is what it looks like. Again, it's a meter with ballistics. It doesn't dance around all over the place, and it gives you a dBm and a milliwatt reading. There are selectable ranges. I use a lookup table to get the linearity. And you can enter calibration factors in. So if you know if you test your source and your sensor and you know it's 50% less sensitive at 7 gigs, you can put that in. You can also program in an attenuator. If you put in a 30 dB power attenuator in front of your sensor, you can program that in and the meter will give you a direct reading of the power. But I must stress this is an alignment tool for tweaking. It's not a tool for doing absolute measurements. You need an HP432 or something like that to do that. I mentioned the signal generator earlier, and we've just talked about power meter. Well, if you combine those two together and a bit of automation, you can make a frequency response sweeper. And that's fairly easily done like this, shown here with LimeSDR, which actually is all that's supported at the moment. I must get round to adding Pluto to this. But LimeSDR, probably through an attenuator into your device, your filter under test or device under test. Probably worth having another attenuator on the output if you can afford it, and then into your power sensor. And the sort of response you can get is this is a 700 odd meg filter I actually use in my ham TV receive chain. And you can see there, you can see 55 dB of dynamic range. There's a bit more available, I think. And you can tweak the filter and you can look at the ripple on the top. It does have some limitations. The scan speed is quite slow, and that's primarily due to the time it takes to move the LimeSDR to each frequency. The LimeSDR will move quickly over small frequencies, but once you're doing a large frequency span, it's a little slower. You can reduce the sample rate in this, so if you're tweaking, you can have a fast, just use 20 samples in the passband, and if you want a nice plot to put in your paperwork, you can use 500 samples. So play with it how you want. You need to be aware that it does respond to spuri from the source, and something like a LimeSDR Mini, the third harmonic is quite high. I've got a couple of old spectrum analyzers, and the CRT is going soft and you can't print from them and so on. So I also built an XY display. Again, this uses the MCP 3002, and it gives you the facility to capture and display a 500 by 400 pixel image, just like the other charts you've seen. And it also gives you the facility to do normalization. So if you are doing a sweep using your analyzer, you can normalize it and then get an absolute reading. So it's fairly simple. Out of the analyzer sockets into the interface, which is the MCP 3002, and then into the Raspberry Pi through through SPI. And this is a plot off my HB8559, and you see that's a lot nicer than taking a photo of the screen, and a lot more convenient than using a plotter. That's the circuit. This is all on the BATC wiki. Very simple circuit. Last item I'm going to talk about is a digital multimeter display and logger. Now, this came about because somebody discovered that the Parkside PDM meter, which is available from Lidl in the UK and I'm sure is available in Germany and other European countries, it only costs £11.99 in Lidl, so I should imagine it's about the same in euros in Europe. You can add an opto isolator to it and get a serial output from it. And this enables you to do a large display on the Raspberry Pi, so you can read it from across the shack, or do it remotely, and I'll come to how you do that in a minute, or to log it. And I built in some battery calculator items. So that's the large display. There you can see it measuring 12.07 volts. And those numbers are an inch, about 3 or 4 centimeters high, so you can see them across the shack very clearly. But when you come to testing batteries, this is a 3-cell lithium battery I tested. You enter either the load resistance or the discharge current, depending if you've got a constant current discharge device. And you say, give it an estimated time. You want it to run for 2.5 hours or something. And you give it a dropout voltage and say when the voltage gets to 9 volts, i.e. 3 volts per cell, or whatever you want to set, turn the load off. So you can then walk away and know that it's not going to kill your battery, but it's going to do a good discharge on it. And this is the discharge curve I got from funnily enough, it was a 2 ampere hour battery. And it came out at 2.06 ampere hours down to 3 volts. So just another facility on there. So let's talk about the test equipment. I'm conscious time's running out. The only other things I'm going to mention is that you can collect from the touchscreen. You can connect to Wi-Fi from the Portsdown 4. So you don't need to have a wired connection. And once you're on the network with your Portsdown 4, you can control it from a web browser or view it from a web browser. Now the only disadvantage of this is the refresh rate is only once per second, so spectrums and the like aren't very smooth, but you can see what's going on. But you can control it while you're in your loft or out in the garden tweaking your aerials from your smartphone. I mentioned the SPI interface. We've designed a standard interface or proposed a standard interface to go on the side of your Portsdown 4 so that you can plug all these utilities, all these bits and pieces into that use SPI. Clearly most of them, the others use USB. So winding up, the Raspberry Pi and its touchscreen give you a very capable platform for doing lots of things. Peripherals do need to be the exact type. It's not like Windows where you can plug in any old audio dongle if you're using a microphone. On this you need the right one. Very nearly all of the software is open source. There is one binary blob in there that's used in the DVB-T setup, but don't get upset about that. The primary information source for all this is the BATC wiki. So the main thing is go out and buy a Raspberry Pi and a touchscreen display and start playing with it. There are future developments coming along. I'm hoping to be able to control the whole thing with just a mouse and using an HDMI display. I'm also looking at Portsdown 5, which is a set of software that will run on the the Raspberry Pi 5 and the Raspberry Pi 4. Clearly, some aspects will perform better on the Raspberry Pi 5. But that's a good year away from being anywhere near as good as the Raspberry Pi 4. Well, with that, I think I've taken up my time. Hopefully there are some demo systems near you there. And look forward to seeing you at Ham Radio in 2025 when I hope to join you. Good afternoon all.